let us look at the Mathieu equation using determinants. This is the equation here. So let me start again. I was doing some calculation, but I'm going to start again here. This is the differential equation. Sometimes people have a 2t there. I'm sorry, 2t, 2 times t here, but we are not doing that. We are just keeping just the cos t. So the stability diagrams that we will get are going to be interpreted accordingly. If you look on the net, you can see stability diagrams for the Mathieu equation like this. This is just from some random source that I have not verified. But what is important is that there is one branch that starts from 0. Think of this as delta, although it says alpha here. Think of this as epsilon, although it says gamma here. So at delta equals 0, there is a branch like this. You can see they are all unstable here in these regions, but there are actually narrow regions of stability, and over here there are fat regions of stability with narrow regions of instability. This is damped, so there are these dashed lines, but the solid line corresponds to the undamped case. And then over here this point is 1/4, which you should be able to connect with, because the natural frequency corresponding to a spring stiffness of 1/4 is half, and that frequency is half of the forcing period. Okay, this one delta is equal to 1. This one delta is actually 9/4, 3 square by 4. This one is 4, which is 4 square by 4. This one is 6 1/4, which is actually 5 square by 4, and so on. So this is the Mathieu stability diagram, and we will see how determinant expansions give us something like that. So over here I will keep only a few terms. I'll keep it up to 6. Okay, so this is my assumed expansion, and then y is cosine of t here. I don't know. Okay, so then I am going to substitute this expression into my differential equation and combine trig. Okay, so I have a shorter expression now because I'm taking fewer terms. Now over here I'm going to do something which is basically like harmonic balance, right? So I'm going to pull out the constant term, and I'm going to pull out the coefficient of cos t. I'm going to pull out the coefficient of cos 2t and cos 3t, and so on. Only cosines are there, as we have discussed in the previous lecture. So pulling out the constant, capital E now, pulling out the constant is just by integration, but from the others it is, I think we will go up to 6. The highest I have is 7, so let me go, but I have integrated up to A6 here, so let me take up to E6. Okay, then I will define, so now there are actually 7 coefficients. There are 1, 2, 3, 4, 5, 6, 7 equations. So I will say that I want linear algebra in Maple, and I will define a 7 by 7 matrix. I was just trying a bigger calculation, but my computer is struggling, so we will go back. 0 to 6, we will take the EQK and just call it temp. We need not have done that. Then from 0 to 6, what we will do is, that means over here k plus 1 is the row here. K goes from 0 to 6, row goes from 1 to 7. In each row we will put the coefficients. Why are we doing that? Because this here is a system of homogeneous equations. All the a's equal to 0 is always a solution. We are interested in a non-zero solution, so we will need a non-trivial solution to this homogeneous system of equations. That means the determinant needs to be 0, so we are collecting the coefficient matrix. Because we have truncated our expansion, therefore we have a finite size determinant. Otherwise we would have an infinite determinant. That is why this is called the method of infinite determinants. Okay, so we're defining it now. Now 0 to 6, 0 to 6 here, that's the 7 by 7 matrix. If we evaluate k, that is what we get here, this matrix. And you can see here that if I put delta epsilon equal to 0, then it's a diagonal matrix. This one here, this one here, this one here. and the determinant is delta times delta minus 1 times delta minus 4 times delta minus 9 and so on. So for epsilon equals 0, the zeros are at delta equals 0, 1, that is 1 square, 2 square, 3 square, 4 square, 5 square and so on. And all this will actually continue in this direction if you can see my cursor towards infinity. But because epsilon equals 0 gives me a known answer, I can use an expansion around some point like delta equals 4 and seek a power series expansion. So to do that, let me just find the determinant. So the determinant Maple has computed, it's some big polynomial. And then what I will do here is I will pose a power series expansion of this type. So I'm starting this one at 4, you see. So when I do that, then I am going to look for these coefficients. I just substitute and then I expand and I go up to 7th order. Okay, and then you will see that I have a coefficient of epsilon. I have a coefficient of epsilon square. All of these things need to be 0. I actually need to find 6 coefficients, so I need 6 equations. So epsilon and epsilon 6. Previously I was doing 7. I'm just taking one less to make sure I'm not missing something bad. And so here it is. I take the coefficients of this expression fa, epsilon to the power k, k from 1 to 6, and I solve for this sequence of ck 1 to 6. Okay, so when I solve that, I get this answer. I get some zeros because it is symmetrical. That's okay. And then I come here, I substitute it into this. I can in fact plot it, but this curve is a bit misleading, because in this one, remember that the delta axis is vertical and the epsilon axis is horizontal. So when you compare here, you expect, since this horizontal is the delta axis and vertical is the epsilon axis, the curve emanating at 4, you expect it to bend to the right, which it does. There are 2 curves here, and this curve is one of them. Okay, now if with more terms or with a bit of care, you can figure out which one it is. I was trying that a bit earlier, but I think I'm not going to do that. If I substitute epsilon equals 2, which is not a terribly large number, then if I evaluate, I get something like 4. Okay, so when I come here, and if I put epsilon equals 2, then I get 4 plus something, some small number. So this is not very bad. But when I start putting larger numbers, I actually need many terms in the power series. Okay, so that's one curve we got. But you know, as we saw here, there are others that emanate. For example, there is something that emanates from 1. Okay, so I can come here and just redo the whole thing. And this one, I look for the solution that starts from 1. Okay, so let me remind you, over here starting from 1, there are actually 2 curves. One bends right and one bends left, right? And out of those 2, we are going to get 1 in this expansion. Okay, so we will collect terms and we will solve, and you see C0, 0, C2 is 5/12. That means that as epsilon increases, delta increases, and so we are getting the curve that is bending more to the right. Okay, if we will get another one where it bends to the left. This is bending right, but eventually bending left, as they all do, and so you see the C4 is negative. You see that is how it will probably bend, and this is delta 1. And we can 1. This is not a very good way to plot for large values, because this polynomial goes up. Actually, there are many terms. If you want to go far into larger values of epsilon, you must use other methods, but we have got a local expansion, at least that you can see. Okay, so this was one solution. I can go back there and I can look for the solution with the signs. no, let me do something else. Let me do the cosine of k minus half times t. So these are the half integers. Remember, we did half integers, but this one should not be there. Okay, so these are half integers, and then when we substitute and expand, once again we get half integers. Why is the constant not there? Because the constant has 0 cos of 0t, that is not a half integer. Okay, so now we come here, we've got all these half integers. This one goes away. Okay, now over here what I have to do is I have to go and say k minus half, right? So now I have these 6 equations, and I come here and this is now 6, and then I come here and this is well, I can just do 0 to 5 and 0 to 5. That should work. Okay, there's a problem there. Why is that? That is because I am looking for n. This n should also be plus 1, because a0 is no longer there. Now that's more complicated. I should have been a bit more careful. Let me just be a bit more careful. The first equation does not have a0, it has a1 and a2, and the next one has a1, a2 and a3 and so on. So over here there is no equation k plus 1. Okay, so that's better. And now you can see that when epsilon is equal to 0, this half, this is bothering me a bit. Why is it there? Well, we'll see. Maybe I hope I have not made a mistake. But there, when epsilon is equal to 0, it emanates from delta equals 1/4, delta equals 9/4, 25 by 4, and so on. Let us look at this one and see. So we will find our determinant, and then over here, for example, if I do 9 by 4, so I've got 9 by 4 and some terms like this. Okay, so 1 by 16 epsilon square and something. So this is what we get. Suppose I come here and put 1 by 4. I have not done this calculation for a while, so this one we need to check. I will check it, and I assume it will be correct. If it is not, I will not post this video. So where are we now? Here, 1/4. Okay, so you see that this one is now 1/4 minus epsilon by 2, and then epsilon square by 8 and cube and so on. So that is what we get here in this curve. What we are getting is this 1/4 minus epsilon is what we are getting here, and this one sort of bends down like this. Some other expansion will give us this one, and we will see that soon enough. Okay, all right, let's come here and look at the one with the signs which are half integers. Okay, now they're all signs. They're all signs. Where are we now? This. They're all signs, and so I can pull out these coefficients, and pull this one out, and you see it is that minus half has come here. This is why it is changing the answer, and that is fine. So I was a bit doubtful, but I am now more confident that I have not made an error. So here is the determinant, and once again you see there is, with the sign also, around delta equals 1/4 then 9/4 there are expansions. So over here if I put delta equals 1/4, I want you to remember something. Previously I had a quarter, 1/4 minus half epsilon. That is what will change. You see now it is 1/4 plus half epsilon. So this is a different curve. Okay. So that is what we have got for half integer signs around here. So we have got half integer cosine gives us this curve, half integer sine gives us this curve. We have got a delta equals 0 from our previous calculation, although I don't think I did that expansion. I did the expansion around 4. Okay, and now finally let us go and do integer sine. Integer sine. And then you see delta equals 1, delta equals 4, delta equals 9. Okay, so then we come here, we've got our expansion. Let us do the one around delta equals 1. I don't know what that noise is outside, I'm terribly sorry. And here is the answer, 1 minus 1/12 epsilon square and so on. And it is in this way that we can get these expansions. I will stop here. You can read Professor Richard Rand's notes, Nonlinear Vibrations. I think he had a clear discussion of this as well.